This is the first lecture in the cybersecurity machine learning workshop. I'm a senior manager at the Joint Security Operations Center at RBC. Our mandate is doing cybersecurity analytics within the bank. That can cover everything from cybercrime to financial crime to risk within the systems, such as identity and access management. My background, I have a PhD in physics. I did my postdoc at Fields in big data. After that, I was working at Borealis for a little while as an applied machine learning researcher. And then I joined the innovation department in RBC doing cybersecurity research. And now I'm at JSOC. Okay, so today we're going to be covering the first topic, which is, well, it's really two topics. We're looking at supervised learning and non-supervised learning. In the first half, we're going to be looking at how to deal with imbalanced data. The applied data set that we're looking at is denial of service attacks. And then we're going to try and do domain adaptation from this trained model to another data set. So one in which we might not have labels for. So we move into more of a non-supervised learning setting. Okay, so let's get started. Before we get into the denial of service, let's have a chat about machine learning and cybersecurity, what it is, why are, these are two very, very hot topics right now, and so how do they intersect? Okay, so applications of machine learning and cybersecurity, they can kind of be broken down into a few different categories. The most common one that you're used to seeing in machine learning anyway is classification or detection. So this could be doing like malware, detecting malware, intrusion events, trying to detect phishing, botnets. All of these things could be at different resolutions. So for example, phishing could be looking at, well, does this URL look fishy? Or what does the actual code of the website look like? Or it could even be looking at the email conversation chain and trying to perform some NLP and determine whether or not phishing is occurring. Another area of machine learning cybersecurity is a big one would be biometrics and authentication. Pretty much every phone now is unlocked using facial recognition. And there's a huge amount of machine learning going into that. The next area where you can apply machine learning would be forensics. So an obvious example of this is threat actor fingerprinting. Say, for example, again, you go back to your phishing. You could try and figure out, well, okay, this threat actor seems to be using this phishing kit. They seem to be from this IP address range. They seem to be targeting these people. They have this modus operandi. But can you figure out a way of clustering malicious actors into groups? The final application of machine learning in cybersecurity is probably in its most nascent stage, is pen testing. And at the moment, I would really just call this more or less theoretical, but there's some research out there in doing reinforcement learning, penetration testing, and turning the threat hunting and pen testing teams into a kind of dual actor game. So it simulates somebody penetrating some network and performing some lateral movement and privilege escalation, and it also simulates an intrusion detection system that is trying to prevent this from happening. But I would say that is very immature at the moment, but you're probably going to see a lot of really interesting things coming in that area. Okay, so there's plenty of applications to work on. Not only that, but you're getting a growing threat space. This is probably one of the most dynamic areas in which you can apply machine learning to, because you're constantly seeing new threats evolving. So Internet of Things devices, they're everywhere now. And so that creates a much larger threat service, but it also can lead to much more distributed attacks. So an example would be a denial of service attack can be distributed by a botnet that is taken over a bunch of poorly secured IoT devices. But IoT devices can also be seen as a point of entry into a system. And the classic example is the casino in Las Vegas that lost all its high roller list because of a poorly secured thermometer in their fish tank. Okay, so social media is another way that the threat space is massively growing. Not only does it lead to things like social engineering and a good way of kind of harvesting information from people, but it's also an excellent method of exfiltrating data. And it's very difficult then to distinguish benign channels from malicious channels if the threat actor is using things like social media to exfiltrate information. The cloud is also a huge risk at the moment. Oftentimes, you're constantly hearing of people having unsecured databases just floating around out there. This is less of a machine learning problem, but it definitely means that there's a lot more things we have to watch out for. And finally, we're seeing lots of new attacks. So ransomware is probably the most famous one lately, but you're also seeing things like cryptojacking, where people are just hijacking your resources to mine for crypto. And we're starting to see evidence of generative ML becoming a threat, where phishing attempts have been made using images created using GAN. At some point, you're going to see a lot more generative models creating text that can be conditioned on certain targets and will probably be very effective. So the challenges that you face in machine learning in cybersecurity, well, labeling is probably the biggest one. You very few data sets in general, very few academic data sets. There's an obvious reason for this. It's poor security to air your dirty laundry and show how perhaps you got compromised. There's also a lot of personal information that you can't share. More information that would again further compromise you. So a lot of these data sets are either anonymized or they're synthetic. On top of that, pretty much every challenge in cybersecurity, every data set that you have, whatever you're trying to do, is going to be on an unbalanced data set, whether it's labeled or not. There's going to be a vast majority of the data is going to be benign. And yes, it's most likely going to be unlabeled. Okay, so heterogeneity is the next challenge. So your data is going to be coming in all sorts of different forms. You can deal with tabular data. You can deal with network graphs. Within that tabular data, you're going to have categorical data, continuous, ordinal, everything. But then in the problem sets or in the problem spaces, say, for example, denial of service attacks, you can have things like concept drift or domain drift, where in one domain, this model works quite well, but in another, it's not going to. An example would be that you have a university that has created a data set for denial of service attacks, and it was trained using university data. Well, that university data is going to look a lot different compared to data coming from an enterprise setting. So you're going to see maybe a lot more Netflix and YouTube in the university. In the enterprise setting, you're just going to see a lot more, say, SMTP or mail data coming through. So this is a huge problem in that everybody's setup is going to be different. Everybody's going to experience different forms of attacks, and it's very difficult to ensure that some data set that you've obtained externally is actually going to perform well in your setting. The next challenge that you can really face is volume. You're generally dealing with the largest data sets you're going to have out there, outside of somewhere like CERN. You're dealing with tera to petabytes in terms of data. Oftentimes this is coming in streaming, so this is a real engineering challenge. And finally, obfuscation. So threat actors don't want to be found, and so they're going to do everything that they can to hide in plain sight. This is a lot more different than, for example, in medical data, where a tumor is going to be obviously quite obvious. Generally, is going to be very obvious compared to the rest of your body, or cats versus dogs. This is going to be quite simple compared to, is this actually a malicious actor or not? Okay, so that's more or less the opportunities within cybersecurity. Let's go on to about what this workshop covers and doesn't cover. So first of all, what does this workshop not cover? We're not going to talk about how to pen test. You're not going to come away as some elite hacker knowing how to break into everything. I wouldn't even presume to be able to teach you this, so we're going to leave that alone. I'm also not going to teach you how to fully secure your network, because I don't want to be liable for that. And I don't, again, it's not my place. I'm not that much of an expert to tell you exactly how you should secure your network. And once more, you wouldn't be able to cover this in such a short workshop. I will not be talking about what vendor tools to use. This is going to take a fairly agnostic approach. I am going to talk about how you probably should interpret outputs from certain tools. Again, I'm not going to specify any tools, but for example, if it starts, what metric should you be looking at if you have a model that is ingesting some data and then outputting some results? Okay, and also not going to talk about why blockchain is going to save us all, because, well, who has time for that? Okay, so what does this workshop cover? Well, how do you deal with unbalanced data? So what are the effective training methods that you can use and employ? And like my previous statement, what pitfalls do you have in the analysis that we might want to avoid? How do you classify without labeled data? So in some cases, you can adapt your data to external models. So in the example that we're going to talk about today, it's going to be denial of service attacks. So you train a model on some source data set, but you have your own target data set. So you want to adapt the source model to a target model that works well with your target data set. And also using negative samples to find anomalies. So in this case, this is really about creating negative data, challenging data for a classifier, getting to classify, is this true or is this fake data? The idea being, if it sees enough of the fake data, it learns to kind of create a border between your possible data and your anomalous data. Okay. And we're mostly going to be dealing with classic data forms that you see in cybersecurity. So tabular data, we're going to be looking at some network packet logs. In the third week, Sahar is going to be covering graph theory. So we get to talk about interesting techniques you can use to find anomalous behavior in graphs. I really wish that was an easier word to say. All right, okay, so let's move on to part one, imbalanced data, pitfalls and remedies. So we're going to be using this with the denial of service attack use case, and I guess I'll get started talking about what a denial of service attack is. So DOS attacks they're attempts to disrupt normal service. So you could be flooding a machine or a network and you're sending in a lot of bogus requests. Typically, these come in at a high volume and frequency. They can come from one source or they can come from a distributed source. So for example, a botnet. And they can be directed at occupying pretty much anything you want: bandwidth, drive space, CPU. The point is to throw a wrench into the day-to-day operations of some website, system, corporation, whatever it is, hospital, whoever it is. An example of DOS being performed recently was a DOS attack on the Telegram app during the Hong Kong protests. Some threat actor felt it was necessary to disrupt protesters from communicating with each other. And like I said, so this can target CPU, it can target drive space, it can target bandwidth. Most people would associate it with high volumes of requests taking up bandwidth, but an example that I quite like is the post DOS attack, where a post request is sent with a very large content length, and then it follows up with a very, very slow upload of the data. So you're sending like 1 byte every 2 minutes. And the idea is if you distribute this and you do this thousands of times, you can really clog up the network. But in this case, this is an attack that's coming at there's a high volume number of people, number of pings, but the frequency is very, very low. Okay. So the first data set we're going to talk about is from the University of New South Wales. And we're only going to focus on a few of the features within this data set. This is because later on, when we do the domain transfer, we want to make sure that these features actually overlap. So we can just very briefly go through the different features that we have here. Duration is the first one. So each row is going to be a flow, and this is going to be a sequence of packets that have been sent from one computer to the other, from a source to a destination. So duration is the amount of time this flow took. S packets is sent packets. So in the first row, you can see 2 packets were sent. Destination packets is saying that those 2 packets were received from the destination. The next column is the inter-packet arrival time. So I guess it's the time between packets. And the same thing for destination. It's the time between packets coming from the destination. Finally, SLoad and deload is just really the bits per second from the source and then also from the destination. And then we have our label saying whether or not this is normal behavior or if this is a DOS attack. As you can see, the class ratio is about 0.2. So this is a slightly imbalanced data set. It's nothing too bad. It's definitely something we can handle. But it's still something to be careful with when you're training a model. And it's also something that we can probably, it's going to create some challenges, and we're going to have to do our best to really squeeze out every last drop from this data. Okay, so on the right here, you can see a very simple neural network that is going to be used to classify this. This is written in PyTorch, and if you're not too familiar with PyTorch, I wouldn't worry too much. The main thing to focus on is the second function forward. So X is our data. We pass the data through a fully connected layer, and then we pass that through an activation function called a ReLU. This gets done again through the next layer, fully connected layer. And again, an activation function is applied. Once more to one final layer, and then a sigmoid function is applied for classification purposes. Okay, so it's a very simple model. There's no bells and whistles here. We're not doing anything like batch normalization or dropout or anything like that. And again, so we definitely could, and the model would perform better, but I want to keep things nice and simple here to help us play around with this and understand the fundamentals. Okay, so here are 5 ROC curves. And these are off from 5 different experiments with this data set and with this model. So here's a challenge for you, looking at these 5 ROC curves. What's different about them? What parameter do you think I changed that caused the variations in these ROC curves? Can you even have a guess? Okay, well, actually, this is a bit of a trick question. Because in reality, the thing that I changed was the ratio of of malicious data to benign data. So you can see in the top left, we've got a ratio of 1 to 1. Then we can see as we progress, this ratio gets bigger and bigger. So we have a ratio of 4 benign data rows for every malicious data row. Then we go from 9 to 1 to 51 to 500 to 1. So ROC curves, for some reason, people like to really extol their virtues when you're dealing with imbalanced data sets, and I cannot understand why. So the moral of this slide is to warn you away from using ROC curves if you were dealing with imbalanced data sets. And if you're in cybersecurity, you almost certainly are. There's absolutely no information you can glean from looking at this. You can maybe tell that the 500 to 1 data set, which is extremely imbalanced, the ROC curve in that case is not so great compared to the 1 to 1, but if you just qualitatively look at them, it's hard to really tell the difference. And I've heard this time and time again. I've seen it in Medium posts. I've heard it in job interviews when people are interviewing for jobs, that they say that they use ROC curves for imbalanced data sets, specifically for that. So why is it such a bad metric? Well, really, it's because it's completely ignoring false negatives. So the ROC curve, if you're not familiar with it, looks at the true positive rate and the false positive rate, but it completely ignores the false negative rate. An ideal ROC curve should have the curve all the way up in the left-hand corner. It has one really great advantage, that if your model is doing no better than random chance, you're going to see a perfectly diagonal line going from the bottom left-hand corner to the top right-hand corner. And that's when you know that your model is completely useless. So in this case, the 500 to 1 model, I mean, it's clearly performing something. And so maybe all of these models are actually performing something. And so why am I being so mean to ROC curves? Well, if you look at something more informative like a confusion matrix, we can actually see that there's a huge drastic difference. So in the 4:1 ratio, which is the one that the data set originally had, we're doing a decent job of predicting denial of service attacks. The false positives are a little high, but the false negatives aren't too bad. As we increase the ratio, false negatives, they actually increase, and that's a problem. And then if we go into the 500-to-1 regime, we've got a completely useless network now. It didn't predict a single denial of service attack. But if you go back and look at our ROC curve, well, looks pretty peachy to me. So this is with a threshold of 0.5, and it does depend on what threshold that you set, of course. But I think the moral of the story here is that there's never going to be one metric that you should rely on. You should be looking at as many metrics as possible. So whether that is you're looking at confusion matrix, you're looking at a precision recall curve, you're looking at your F1 score, even if you're looking at your accuracy, you need to take this into account from multiple perspectives, okay? On top of that, the threshold that you end up choosing is obviously going to be very, very important and can vary according to the ratios that you're dealing with. Okay, so let's move on to how you can actually improve imbalanced training. So a lot of solutions out there involve data augmentation or upsampling or downsampling. Data augmentation is great if you can do it, and 9 times out of 10, it's very difficult to do that in cybersecurity because you have very heterogeneous data, it's categorical, it's very hard to generate something that is realistic. It's very easy when you're dealing with images to just permute the image, skew it a bit, rotate it around, whatever. But it's not so easy to do that with real-world data, such as packets, network packets. So you can do upsampling or downsampling. I'm not a big fan of doing that because you can end up adding too much importance to an area of the distribution that's actually not so important, or vice versa. You could end up reducing an area of the distribution, minimizing that area and making it seem less important than it actually is. So today we're going to talk about class weights, and this is a much simpler approach. It's one line of code, so you're not worrying about how to sample your data. You're not worrying about generating data. All we're really trying to do is bias the classifier. So we're trying to ensure that the cross entropy loss that we're using, the loss function that we're using to classify between benign and malicious data, is tuned to, is optimized as best as it could be. Okay, so this equation here, we have the binary cross entropy loss, and we've broken it down into 2 portions. The left side of the first term in the equation is the cross entropy loss for the case when the truth label is 1, and the second term in the equation is when the truth label is 0. Okay. So one thing that we can do to improve this is by adding on just an extra multiplier term. So alpha in this case is going to multiply by the first term and augment the loss coming from any misclassification related to the malicious data. Contrary to that, you're going to have 1 minus alpha, which is going to somewhat minimize relatively to the first term. You're going to minimize the second term so that it's not as much of a problem if it misclassifies benign data as malicious. So what you're trying to say to the classifier here is focus on malicious data. I'm going to punish you a lot more if you get those ones wrong. Okay. So what values do you set alpha to? Alpha here could be related to the imbalance of the data. So in our case, we have a ratio of malicious to benign is 0.2. So we could set alpha to be 0.8. Okay. And then we would set 1 minus alpha then to be 0.2. So this means that you're going to have the loss coming from the malicious data to be 4 times larger than the loss coming from the benign data, okay? And this can really, really help improve your model. But you can do more than this. You can also start playing around with the shape of the cross-entropy function. And to deal with this, there's a paper called focal loss. So focal loss is a slight modification of the binary cross-entropy function. And it was originally used in object detection. And it was for, similar applications like YOLO, where it's one-shot classification or object detection, one-shot object detection. But you can adapt this very, very easily towards any classification problem here. And here we're just going to look at the binary cross-entropy case. As you can see in this figure, we're seeing multiple curves going from a value of gamma is equal to 0 to value of gamma is equal to 5. So the case where gamma is equal to 0, this just returns the regular cross-entropy function. So then you can see as you increase gamma, the loss function as a function of the probability of ground truth class. So what that means is, okay, so it's the model is predicting a value, and in the case of this actually being the value 1, so let's say, for example, it predicts 0.8, then it's almost correct, right? And if it predicts 0.4, well, that's actually not very, very good. So the idea is that we're trying to squish down this function so that when a model is predicting values that are close to 1, it doesn't get punished as much as when it's predicting values that's far away from 1. The idea of this approach is that you're trying to get the model to focus on challenging data samples. Data samples that are very easy to classify, it doesn't get a whole lot of reward for it because it was a gimme, right? Excuse me. Okay. So let's put the focal loss and the class weight into practice. We can put these two in conjunction. So I did a grid search on the denial of service attacks, iterating through many parameters of gamma from 0 all the way up to 2, and then iterating over many values of alpha from 0.5 all the way up to 1. Here we have the plot of the precision recall curves for each iteration. What's interesting is, so you can see that shoot, I have the labels wrong. Okay, so let's be clear about that one. So red here is the best performing, and it should say that gamma is equal to 2 for that, and alpha is equal to 0.8. So alpha here, the optimal value of alpha actually represents the data distribution, so that's good. Gamma equal to 2 is also the recommended value from the focal loss papers, so it's also good that it's performing well at that level. Meanwhile, if you set the alpha rate too high at 0.9, and if you set the gamma too low, you can get a very low performing model. So you can see huge difference in performance here. So this is with the same data set in each case, the same parameters, the same number of epochs, but by just tuning these two small parameters, you can get a massive variation in model performance.